Hello, I'm Michael O'Connell, and in today's video, I wanted to talk about a couple topics that I've learned in organic chemistry that I think will be very relevant in future videos. And the first of those topics is going to be nucleophilicity. So, we observe that nucleophilicity decreases as we move from left to right across a period. This is the opposite trend that we see for electronegativity, and that's because more electronegative atoms are more effective at stabilizing negative charges. So when we move down a group, we actually see that nucleophilicity increases, and that's because the electron clouds are bigger as we move down a group because we increase in energy level. And this makes the electron clouds more polarizable and allows them to more effectively delocalize negative charge across a larger area, which is very effective at stabilizing atoms or compounds. Now that I've explained the trends for nucleophilicity, it would be remiss if I didn't mention the trends for basicity. And contrary to what you might think, the trend is not always the same. So when we move from left to right across a period, basicity does decrease, just like nucleophilicity. However, when we move down a group, basicity actually does decrease, because when we think about basicity, we need to remember that we are considering the compound's ability to remove a proton. And we also need to remember that when we talk about nucleophilicity, we are going to need to ask ourselves what ability the compound has to donate an electron pair. And you might think that that sounds familiar, and it probably does, because I learned in general chemistry that a nucleophile is also a Lewis base, because that's what donates an electron pair, and the compound that receives the electron pair is the electrophile or Lewis acid. So you can kind of see things coming together from the past as well. Now, what about leaving group reactivity? That's the third topic I really wanted to talk about here. And leaving group reactivity follows the opposite trend of basicity and nucleophilicity when we're talking about moving from left to right across a period, which makes sense because, as I said before, more electronegative atoms are more effective at stabilizing negative charges. Thus, they can be more effective leaving groups when they leave a compound. The one exception to this is fluorine, and that leads me into the second trend for leaving group reactivity, which is that leaving group reactivity increases as we move down a group, which also has to do with atomic size, just like nucleophilicity. So the one thing that you can maybe take away from this when you're studying for your exams and then when you're taking your quizzes and exams is that leaving group reactivity is always the opposite of basicity. So weak bases make great leaving groups and strong bases make poor leaving groups. For instance, OH minus or OH, an OH group on a compound, is going to be a very poor leaving group because it's a very strong base. However, water, so if you have an OH2 plus on a compound, that is going to be a very good leaving group. After those explanations, hopefully you have a better understanding of the trends we observe for basicity, leaving group reactivity, and nucleophilicity. Now I would like to talk about what's on my screen. And it is going to be very important when you're doing substitution and elimination reactions to figure out if you have a strong nucleophile or if you have a weak base. So our first column here, we have strong/strong. So these are compounds that are strong bases and they're strong nucleophiles. And the first thing that pops into my head when I'm given one of these reagents is that I'm probably not going to have an SN1 or E1 reaction. But of course, that's not always the case. However, it is just something to keep in mind because we know that because a relatively stable carbocation, at least secondary or tertiary carbocation, has to be formed as an intermediate in an E1 or SN1 reaction, we know that we can get away with having a weak base or weak nucleophile. So that's very important for us. Now, this second column is probably my favorite. I love these compounds because they make my life very easy. Because they are very, very big, they have negative charges, and they are very strong bases, but they're weak nucleophiles because they're so large, as I said. So they're very sterically hindered. What this means is that they're pretty much going to be an E2 reaction. And these are going to be very important, especially if you have a primary alpha carbon, that is the carbon bearing the leaving group. The only instance in which that's not going to be an SN2 reaction is probably when you just have a super weak nucleophile but a very big strong base like LDA or terp butoxide with the potassium salt there. So I really, really like those. So always look out for those easy points that you can get in a very hard course like organic chemistry. Now we have this column over here. So we have strong nucleophiles and weak bases. The thing that I would stress here is just remember that the trends that we just talked about. I think sulfur with, some sort of negative charge, that's the one that I find to be very common because your professor probably really wants you to understand that when you move down a group, basicity decreases, right? So you have RS minus as a strong nucleophile, but a weak base, but RO minus is a strong base and a strong nucleophile. So that's a very, very important thing that I must emphasize because you're probably going to see it. It would not surprise me at all. The other thing that is very common in this third column are going to be your halogens. So when they form anions, so I minus, Br minus, Cl minus. Hopefully I did mention, I think I did before, that fluorine is a poor leaving group. So there's that. But those are going to be strong nucleophiles because they have, well, if we're talking about the halogens, they're going to have 8 electrons, so 4 electron pairs. So they're definitely going to be able to donate an electron pair and form a bond. However, they are weak bases. Now, why are they weak bases? Well, if we think back to what we probably learned in general chemistry, is the stronger the acid that you have, the weaker your conjugate base. So hydrochloric acid, for example, is very strong. It breaks up into its ions very easily. But that means that the Cl minus anion that is formed is a very weak conjugate base, meaning that it's not going to readily grab a proton off of another compound. So that's very important for us to realize, and that's what we see with the cyanide ion as well. In the last column, we have weak bases and weak nucleophiles. And this should always alert you to the fact that you're probably going to have an E1/SN1 mechanism occur. And oftentimes they will both occur. The only times in which they don't always occur together are when we do reactions with alcohols, and perhaps we will look at those in future videos. But for all intents and purposes here, we need to understand that they are weak nucleophiles and weak bases, first of all, because they don't have that negative charge that we're always looking for, right? They typically are pronated, so we have ROH, H2O, water, right? And then carboxylic acids as well. So basically, once again, because that carbocation intermediate is formed when you have an E1 or an SN1 reaction, you just don't need a strong nucleophile because that carbocation is relatively stable enough that it forms, but it's quite reactive. So you just need that lone pair of electrons for your SN1 that will form a bond to that carbocation intermediate. And then for the E1, it's going to be where your weak base will rip off a proton and those electrons will fill in and usually form some double bond. Now, the last thing I want to talk about here is in the bottom, it kind of groups everything together for us, which I think is really nice. Nothing really jumped out at me too much except for one thing, and that's this H minus anion. It's not something you see very often, but it was something that I did see in one of the problems I was working on the other day, and it kind of threw me for a loop a little bit. Because what I had to remember is that H minus, even though it is very small and it has that negative charge, it's not going to be a strong nucleophile. Okay, so a hydrogen is not just going to like add in there and form a bond with that lone pair of electrons that it has. It's actually going to pull off a proton. I think that does make some sense because we know that obviously H2 gas is very stable as a diatomic molecule. So that is just something to remember. I think you would most commonly see the H minus with usually a sodium ion. So that just might be something that you need to remember for your exam as well if your professor wants to try to make sure you really, really know your stuff. So obviously this stuff can be very difficult because it involves a lot of concepts that you have to know and understand, but also a fair amount of memorization. So you do have to take courage in that. I know it's not easy. It hasn't been easy for me as well, which is why I'm making this video to help you as well as myself get through organic chemistry. Although I find it very interesting, it's definitely a hard course, and I just want to help people as best I can. So I hope that this video was helpful for you. And if it is, and you know other people who need help in this course, please share this video. That would be awesome. I just want everybody to do the best that they can in this course and really understand it and maybe have a little fun along the way. So thank you so much for watching.